Okay, hopefully you're still with me. I was going over. Sorry, let me detach this. I was going over. Whoops. Did I delete something? Let's bring this back. This thing is always so. Yes, I did delete something. Okay, I was going over this example. So we started with g of s is equal to 500 divided by s plus 1 times s plus 3 times s plus 10. So let me try to detach this keyboard without deleting anything. Okay, good. Okay, so we got up to this step where we're ready now to multiply by the complex conjugate. So that's actually this step right here if you're following along in the lecture notes. Okay, so we are going to multiply the top. So we get 500 times 30 minus 14 omega squared minus j 43 omega minus omega cubed divided by, now the nice thing about multiplying by the complex conjugate is the imaginary part will cancel. So we're left with the real part squared minus the imaginary part squared. Okay, so this allows us now to separate the real part from the imaginary part. So the real part of g of j omega is going to be equal to 500 times 30 minus 14 omega squared, all divided by our denominator. I'm sorry. So this is 30 minus 14 omega squared quantity squared minus 43 omega minus omega cubed quantity squared. And, sorry, our imaginary part is of g of j omega. Let me write this clearly. Is negative 500 times 43 omega minus omega cubed, all divided by, again, the same denominator. Okay, so just to double check here, this is the exact same thing that we're getting. Okay, and this is our real part, and this is our imaginary part. Okay, so now that we have the real part and the imaginary part, we're ready to create this table. Okay, so this one is a little bit tricky to do by hand, and I recommend you double check this with the calculator, but this is how it goes. So again, we start with enumerating different values of our frequency. That's this omega. And we're going to plug in omega for our real part to get this column. And then we'll plug in omega to our imaginary part to get this column. Okay, so that's where this is coming from. All right, so if we start with 0 and we end with infinity, and then you can always pick a few test points in between, and we can actually pick these test points to be kind of strategic, and I'll talk about that in a second, but always start with 0 and always end with infinity. So if we start with 0, we plug that in. Our real part happens to be this 500 over 30, which is the same as 50 divided by 3. So this is our starting point. Okay. Then let's plug in for omega equals infinity. Well, at omega equals infinity, our real part just happens to be 0, and our imaginary part here and here happens to be 0 as well. So this is our ending point. So this is omega equals 0, and our end is omega equals infinity. So, we have these arrows going around this way. Okay, but what about these 2 points? Okay, so there is a very strategic way to get these middle 2 points. And that's actually by fixing the real part of g of j omega. Suppose we fixed it to 0 and we solved for omega. And then we took that omega and we plugged it into the imaginary part of g of j omega. Then we would get this negative 8.36. Okay, and our omega is actually going to, when we solve for the real part equaling 0, we get omega to be 1.46, okay? So that's where this point is coming in, because our real part, this is again our real part, and this is our imaginary part. The real part is 0, and so we get just a single imaginary part at this negative 8.36. So that's how we get this point. Now, similarly for this guy, we're actually going to fix now the imaginary part to 0 and solve for omega, which turns out to be this guy, 6.55, and then we're going to plug this in to the real part now of g of j omega. Okay, and when we do that, we get this negative 0.87. Okay, so that's where this point comes. So we're going around, we hit this point, then we hit this point, and finally we end at this point. So sorry. Don't know how to do that. Okay, so this is what our Nyquist diagram looks like. Now, we add in this dotted line because this is the mirror image of our solid line here on the bottom. Okay, and that's how we are able to find... Oh, no, come on. This is just not cooperating as usual. So bear with me. Okay. So that's how we're able to get... Oh, you're being so good. Now you're being difficult. Why? But anyway, this is how we are to get the Nyquist diagram and these rotations. And you see that because we're at this negative 0.87, again, negative 1, and it won't let me draw for some reason. Come on. Behave. Doesn't want to cooperate some days. Today is just not the day for this. Let's go back. Oh, I went to the very beginning. What happened to my view here? Okay, here we go. Okay, so you see how this is at negative 0.87, so our negative 1 is out here. So again, for this example, n is 0 because there are no rotations around negative 1, and we started with s at negative 1, s equals negative 3, s equals negative 10, so the poles are this, so there are no right-hand poles. So that means that our P is 0. So this should also be a stable system. Okay, we have one more example. This one is a little bit easier. I will do this one again on the OneNote. Oh, come on. Let's go to the OneNote here. This is our third and final example, and I'm going to separate this keyboard one more time. Sorry for all the noise. Okay. Here we go. We're ready for example number 3. Okay, and just to be sure, we have 1 over s times s plus 1. So our g of s is equal to 1 over s times s plus 1. Okay, and again, we're looking at the frequency response. That's what we've been focused on all this week. And the frequency response, we fix s equal to j omega. Now today we're talking about the Nyquist diagram. In the Nyquist diagram, we need the real and the imaginary parts of our g of j omega. So in order to get that, we plug in for j omega, we get 1 over j omega times j omega plus 1. And again, we need to eliminate the imaginary part in the denominator. So we're going to multiply by the complex conjugate of both of these poles on the top and the bottom. Okay, so if we do that, let's multiply everything out. We get j omega squared plus j omega times, this whole thing again. Okay, so this is equal to 1 over j omega, and j squared again is minus 1. So we have minus omega squared. And if we multiply this on the top here, we get minus a minus times a minus is a plus, j squared omega squared minus j omega. Similarly on the bottom, so j squared omega squared minus j omega. Okay, if we simplify this, we get 1 over j omega minus omega squared. And so you see here, j squared is minus omega squared minus j omega. So this is indeed the complex conjugate of this guy. I can rewrite it so you'll see it more clearly, but if I just flip the order here, minus j omega minus omega squared. So this is indeed the complex conjugate. Okay, so let's keep going. We're going to multiply now this guy by this guy. So our numerator is minus omega squared minus j omega divided by our denominator. So we get minus j squared omega squared, and then the imaginary parts are going to cancel, and we get plus omega to the 4th. So let me just write this out to show you what I mean. So we did this one, and we did this one. Now let's do j omega times minus omega squared. So we get minus j omega cubed, and then we get minus minus omega squared times negative, so this becomes a positive j omega cubed. Okay, so hopefully you see that when we multiply by the complex conjugate, the imaginary parts cancel. So that's why we're multiplying by this complex conjugate. Okay, so this is what we are left with in the end. So minus j squared is actually going to be plus omega squared plus omega to the 4th. Okay, let's just double check that. Right, so this is what we should get here. Okay, so our real part is this guy, minus omega squared divided by omega squared plus omega to the 4th. And we can simplify this, so this will become, if we pull out omega squared. We get minus 1 divided by omega squared, 1 plus omega squared. So something like this. So these will cancel. So the real part, we're left with negative 1 divided by omega squared plus 1. So that's where this is coming from. Okay, and for the imaginary part, we get minus omega divided by omega squared plus omega to the 4th. So again, we can factor out an omega, so we get a minus 1 on the top. And if we factor out an omega on the bottom, we get omega plus omega cubed. Okay, so these two omegas will cancel, so we're left with minus 1 divided by omega plus omega cubed. So this is the imaginary part, and again, we can double check this. So we get the same thing. Okay, so let me go back here, sorry for a second. So now we're ready again to make this table. Okay, so let's make it here in our OneNote just to go through this process one more time. So we're going to enumerate values of our frequency omega, and we're going to compute values of the real part and values of our imaginary part. Okay, so again, we always start with 0, and we always will finish with infinity. So for the real part, so let's plug in for omega equals 0. The real part of j omega is equal to negative 1 divided by 0 squared plus 1. So this should give us negative 1. And now for our imaginary part, imaginary part is equal to negative 1 divided by 0 plus 0 cubed. So this should be infinity, because anything divided by 0 should be infinity. So let's just double check. So that we have negative 1, and this negative sign will make this a negative infinity. So if we start to make our Nyquist plot, we have the real part, we have the imaginary part. So we start at the real part of negative 1, and then the imaginary part is going off towards infinity. Okay, so this is our starting point. Kind of an odd starting point, but that's okay. Okay, now let's compute for, and let's see if I have enough room. Omega is equal to infinity, so our real part is going to again be, this is our real part, negative 1 divided by omega squared. So we have negative 1 divided by infinity plus 1. So this should give us a 0. So anything divided by infinity is 0. Okay, and then the imaginary part at omega is equal to infinity is given by negative 1 divided by infinity plus infinity cubed, which is kind of weird, but again, this should be 0. Okay, so our ending point is here at 0. Okay, so it's going to have some kind of behavior like this, and so in a reflection across the x-axis, we get the following. So this is our Nyquist diagram. So again, no rotations around 0 here. And our poles, to start with, we're at -1 and 0. So again, no poles in the right half plane. So this should be a stable system. Okay, so these are... Oh, and I'm sorry, it seems like I'm reversed this. This should have been -infinity. So actually, -infinity is down this way, isn't it? So this would be reflecting this way. Okay, anyways. Just a simple reverse of sign here, but it really doesn't make a difference because we reflect across the real axis, and so that's why we get the same kind of thing. Okay, anyway, so this is how we will plot the Nyquist diagram. So let's move to talking about the gain and the phase margin. So we talked about this briefly for the Bode plot. I just want to remind you what this is all about. So gain and phase margin is all about stability. Okay, remember that stability is very important. A system has to be stable before we can design a controller to improve it. Okay, and for a system to be stable, all the closed loop poles have to be, remember, in this. If this is our S plane, then all the closed loop poles are in this left half plane. Something like this. If we have any poles in the right half plane, like over here, this means that our system would be unstable. Okay, but as long as they're in this left half plane, then we're good. Excuse me. Okay, so we talked about these conditions for the Bode plot. For systems with no right half plane poles, the magnitude is less than 0 decibels, where the phase is at plus or minus 180 degrees. And it's the opposite. For the system to be stable, it has to be greater than 0 dB if there are right half plane poles. Okay, and then at the beginning of this, part 1, if you go back to the video on part 1, we talked about this Nyquist criterion. We talked about the P, meaning the number of poles of G times S or G times H in the right half plane. N is the number of counterclockwise revolutions around -1 on our Nyquist diagram. And so adding P minus, subtracting N from P gives us the closed loop poles. And this is the number of closed loop poles in the right half plane. So this Nyquist criteria tells us whether a system is stable or not. Okay, so what is an unstable system? I mean, you have seen this in the real world, and you've probably seen this more recently in today's day and age. Especially with watching the news or things on TV, but you probably have seen videos of a bridge collapsing because of wind, forcing the bridge to actually, it will oscillate, and it oscillates actually at what's called its resonant frequency. And basically when it does this, it will actually cause a system to be unstable. There's a similar kind of theory, or maybe a better word is hypothesis, that physicians believe that the brain is when it undergoes a seizure, there are some that believe that this is like the brain experiencing an instability. So this is still kind of disputed in the clinical world, but researchers have tried to actually mathematically represent a seizure as an instability in linear systems. So kind of interesting. So anyways, again, you think about unstable systems, this is what we're talking about. you get this clear deviation in the time domain where um, this is looking at the current, but it could be any variable that we're talking about. Could be the position of, the bridge, or any signal that you're measuring. As time goes on, this signal actually will go, towards infinity. And so this is what an unstable system looks like in the time domain. And we can quantify stability again in the frequency domain. So that's what we're talking about. So we can quantify stability with the gain and phase margin. So we're going to see that in the Bode plot and in the Nyquist diagram. Okay, so here is kind of the technical definition. Systems with greater gain and phase margin can actually withstand greater changes in the system before becoming unstable. So it's, in a sense, if it has a larger gain and phase margin, that means that it's more robust, meaning that you can perturb the system or you can change the parameters slightly and it's still going to be stable. On the other hand, if you have a smaller, this thing likes to play tricks on me. If you have a smaller gain and phase margin, then your system is more susceptible to being unstable. Susceptible, that's a hard word to spell. Susceptible to instability, let's say. Okay? So that's why it's important. You want to have a system with a larger gain margin, obviously, and larger phase margin, because then your system is going to be able to withstand more uncertainty from the environment. And we always can expect uncertainty from the environment because there are just things that we cannot always control. Things like changes in, the environment, whether it be, changes in the temperature, which might affect, the parameters of your system. You think about how, changes in the temperature might affect the capability of the damper or the spring in a mass spring damper system, or maybe it will slightly change the the resistance of your system in the LRC circuit. So, there's different things that can happen, and, you just want to be able to account for that. And so designing a system with a larger gain and phase margin is ultimately going to benefit your controller in the end. Okay, so what is it exactly? It's the amount of change in the gain expressed in decibels required at 180-degree phase to make the closed loop system unstable. Okay, we'll go over this here in a second, but this is the amount of change in the phase required at unity gain to make the closed system unstable. So what is this really trying to get at here? Okay, so we saw this for the Bode plot, right? We're talking about the magnitude being below that 0 dB, which we talked about was 0 dB corresponding to a magnitude of 1. And so, when we had our phase plot at 180 degrees, that's where we saw this gain margin. So our phase, looked like this. Let's see. So this was that phase margin. Anyway, we can go back to this, but that's kind of, oh yes, it's here. Great. So this is the idea. Okay, you have this 0 dB, which remember corresponds to a magnitude of 1. And we have this 180 degrees. So again, this goes back to, we were talking